Welcome to the Frontiers of Physics lecture series. This is our attempt to bring the excitement of physics to the community. It's a great idea that was brought to me by Patrick O'Hara and his wife Katerina Randolph, who unfortunately couldn't make it today. But with a generous donation from them, they made this lecture series possible. Normally, scientists have to work really hard to catch a donor's attention. Here was the opposite way. He had to try to get through my email screen where I don't read email from people I don't know. And he said, I really want to see a public lecture series going. But he finally got through. So this series is very important to bring scientists and the community together. There are all sorts of amazing ideas behind the very mundane technology that's in your pocket. The ideas of, I think 1,000 years from now, if people look back to the 20th century, they're going to say that's the century when quantum mechanics was discovered. It was a completely new idea that just is a landmark in the history of human thought. And it's a gift that keeps on giving, and it makes your computer work and your phone work. But today we're going to hear about a completely new wave or avalanche that's about to descend upon us, this quantum information science. And Seattle is one of the epicenters for that, with Microsoft putting an enormous effort into this just across the lake. Today I want to thank both them, and I also want to thank a graduate student here named Natalie Clow, who helped put together a study guide, which was made available on the website and sent to an email. And if you get intrigued by the lecture and want to learn a little bit more, you might go back to that website and look at the study guide she put together, which is designed to be accessible to people who've never taken a class in quantum mechanics. So, like Patrick and Katerina, you too can get involved. I feel a little awkward asking people for help, so I would like each of you to tell the person sitting next to you that there are donation envelopes outside the door when you leave. But there are other ways of getting involved too. You can, if you just want to find out more about science, if you want to see somebody's experiment, you should contact the physics department. You'd be amazed at how much and how long physicists can talk about their work to complete strangers. So we have these lectures twice a year. This is the third one here in Kane Hall. A year ago, we had David Gross, the 2004 Nobel Prize winner, talk about the future of particle physics and string theory. And last fall, we had Rainer Weiss, the discoverer of gravitational waves, or one of the co-discoverers, who came and gave a talk and will likely win the Nobel Prize next fall. And we don't have the fall lecture settled yet, but you'll get information about it in an email if you registered for this lecture. We have these lectures filmed by UW-TV, so you can revisit them, or you can send a link to your friends if they want to watch it. So one of the pleasures of introducing Rainer Weiss last fall was the rather unusual trajectory he took, where he failed college, I think several times before he got on track. This year's speaker is a paragon of success. John Preskill is the Richard P. Feynman Professor at Caltech now, and he's the head of he's the director of the Institute for Quantum Information and Matter. He got his bachelor's in Princeton and a PhD at Harvard, and then he was a postdoc at Harvard, and he was snatched out of that very quickly, where they made him an assistant professor, and that's where I met him when I was a graduate student, and he was probably the best lecturer I had as a graduate student. And what was amazing is, as a beginning assistant professor, when most professors are completely crushed by the weight of teaching and they're terrible lecturers and they have a hard time handling all that material, he gave a specialty course on all of what's called the strong interactions, a very complex subject with many, many different facets. And his lectures explored every one of them in beautiful detail. And what really impressed me is that all his lectures were handwritten and nothing was crossed out. Everything just flowed. It's like Mozart. Anyway, so he's a hero of mine, and I was really pleased that he agreed to come here and tell us about quantum information science. Thank you.
Well, thank you very much, David. I remember David as a very eager graduate student in those days, and it was kind of you to remember the lectures. Of course, the trick is when you make a mistake, you start over again on that page so you finally get it right. So I'm going to be talking about quantum physics in this lecture, but also about information. Now, we all know that information has a profound effect on our daily lives. We have information technologies that are ubiquitous, but we realize that those information technologies are destined to be replaced by new ones, which we can scarcely hope to imagine today. But it's kind of fun to wonder about future technologies. I may not be the ideal person to speculate about the future of technology. I'm not an engineer, I'm a theoretical physicist, and I can't claim to be deeply knowledgeable about how computers really work. But as David said, as a physicist, I know that the crowning intellectual achievement of the 20th century was the development of quantum theory, and it's natural for physicists to wonder how the development of quantum theory in the 20th century is going to impact 21st century technology. Quantum theory is an old subject by now, but some of the deep ways in which quantum systems and classical systems differ from one another, we've come to appreciate only relatively recently, and a lot of those differences have to do with properties of information carried by quantum systems. To a physicist, information is something that you can encode and store in the state of some physical system, like the pages of a book. But fundamentally, all physical systems are really quantum systems governed by quantum mechanics. So information is something that we can encode and store in a quantum system. And physicists have appreciated for quite a long time that information carried by quantum systems has some notoriously counterintuitive properties. That's why we like to speak of the weirdness of quantum theory. But in recent years, we're taking more seriously the idea that we might put the weirdness to work to exploit the unusual properties of quantum information to perform tasks that wouldn't be possible if this were a less weird classical world. And that interest in putting weirdness to work has driven the emergence of a field we call quantum information science, which derives much of its intellectual vitality from three central ideas: quantum entanglement, quantum computing, and quantum error correction. And the goal of this lecture is to explain those ideas to you. But I'd like to start at the beginning. As you know, we can express any amount of ordinary classical information in terms of indivisible units, bits of information, or you might think of a bit as a physical object, let's say a ball, which can be either one of two colors, for example, red or green. And because bits are valuable, sometimes we like to store them, I can put a bit inside a box, and then later on, when I open the box, the color ball that I put in comes out again, so you can recover the bit and read it. Well, by quantum information, I mean information carried by a quantum system. And for quantum information as well, we can express it in terms of indivisible units, what we call quantum bits, or qubits for short. And for many purposes, it can be useful to envision the qubit, again, as a colored object stored inside a box, but where now we can open the box in two complementary ways, corresponding to two different ways that we can prepare the state of the box or observe the box. I can put a ball into either door number 1 or door number 2 of a qubit, and then later on, if I open that same door again, the color ball that I put in comes out again, just as though it were a classical bit. But if you put information into a qubit through door number 1, and then later on you open the complementary door, door number 2, then what comes out of the box is completely random, has 50% probability of being red, 50% probability of being green. It doesn't reveal any information about what color you originally put inside the box. So in order to read the quantum information, you have to do it the right way. If you open the wrong door, you'll damage the information, and it's not possible to recover from that damage. So you can think about what that means if I want to copy quantum information. If I had a quantum copy machine that could perfectly copy a qubit, that would mean that I could put information into door number 1 of a qubit and then make a copy of the qubit. And when I open door number 1 on the original and the copy, the color that I put in should come out of both boxes. And likewise, if I had stored information through door number 2 of the qubit, and then made a copy, and later on opened door number 2 for the original and the copy, the color I put in should come out of both boxes. But in fact, no such copy machine for qubits is physically possible. It's not allowed by the principles of quantum theory. And the reason why is that in order to copy the qubit, you have to probe inside the box. And if you look in the box through the door that I use, then you can copy the information just as though it were classical. But if you use the wrong door, then you'll damage the information, and there won't be any way to build a high-fidelity copy. So you might be able to clone a sheep, but we can't clone a qubit. Now, as you've seen, I like to think about these qubits in abstract terms, the way we often think about bits. But a qubit always has some physical realization, and I'm going to mention some other possible realizations later in the talk. But for now, just so you have something concrete to think about, a qubit could be carried by a single photon, a particle of light. The photon has an electric field which could be either oriented horizontally or vertically, which correspond to the 2 possible states we could see if we look through door number 1, or we could consider the electric field oriented along the 45-degree rotated axes, which correspond to the states we would see looking through door number 2. So if we prepare, for example, the horizontally polarized photon, and then we observe the polarization along the tilted axes, then we'll just generate a random bit, with either outcome occurring with probability 50%. But the really interesting ways in which quantum information is different from classical information, we can appreciate only if we consider states of more than 1 qubit. So let's imagine we have 2, and they could be far apart from one another. Let's say one is at Caltech in Pasadena, where I come from. The other is in the custody of my friend in the Andromeda galaxy. And some time ago, these 2 qubits were both on Earth, and they interacted in a certain way, which caused them to become correlated with one another. And that correlated state has some unusual properties. Namely, I can open my box in Pasadena through either door number 1 or door number 2, and either way, what comes out of the box is just a random color. Could be red, could be green, with the same probability. And the same is true for my friend in Andromeda. He can open the qubit through door number 1 or door number 2 and just sees a random bit. So neither one of us, by opening our boxes, gains any information about what's inside the boxes. We just generate a random bit. And that's kind of strange, because with 2 qubits, we should be able to encode 2 bits of information. But where has that information be hidden? Where has it been hidden? And the answer in this case is that the information resides entirely in the correlations between what happens when you open a qubit in Pasadena and open it in Andromeda. Because it turns out that if I open my box through door number 1, and my friend opens his box through the same door, then we're guaranteed to find the same color. It might be red or it might be green, but if we open the same door, it's always the same. And that's true also if we both open door number 2. What we find might be red or might be green, but when we open the same door, we find the same thing. And we know this is true because we've done the experiment millions of times using identically prepared pairs of qubits in this particular state. Now, there are 4 perfectly distinguishable ways in which the box in Pasadena could be correlated with the box in Andromeda. That is, we could see either the same color or opposite colors when we both open door number 1 or we both open door number 2. That's 4 possibilities. We've chosen one of the 4. That's 2 bits of information that's encoded in the boxes. But what's unusual is that that information is inaccessible locally. We can't see that information when we look at the box in Pasadena or in Andromeda. It's entirely stored in the correlations between the 2 qubits. And that property of quantum information, that it can be stored non-locally, shared by distantly separated objects, is what we call quantum entanglement. And it's the really important and deep way in which quantum information is different from classical information. Now, correlations themselves are not unusual. We encounter them all the time in daily life. My socks are normally the same color, so that means if you look at my left foot, then you know without looking what color sock to expect to find when you look at my right foot. And you might say it's pretty much the same thing with the boxes, isn't it? Because if I want to know what my friend is going to see when he opens door number 1 in Andromeda, I can open door number 1 in Pasadena to find out. And if I want to know what my friend will find when he opens door number 2 in Andromeda, I can open door number 2 in Pasadena to find out. So you might say, aren't the boxes just like the sockses? But in fact, I insist that the boxes are fundamentally different than the sockses. And the essence of the difference is this. There's just one way to look at a sock. But because we have more than one complementary way of viewing the box, the qubit, the correlations among qubits are richer and more interesting than the correlations we encounter in everyday life. Now, this phenomenon of quantum entanglement was first explicitly discussed over 80 years ago by Einstein, Podolsky, and Rosen. And to Einstein, quantum entanglement seems so unsettling as to indicate that something's missing from our current understanding of the quantum description of nature. And that paper elicited some interesting responses, including one from Schrdinger that was especially insightful. And Schrdinger put it this way. He said, the best possible knowledge of a whole does not necessarily include the best possible knowledge of its parts. What Schrdinger meant is, even if we have the most complete description that the laws of physics will allow of that pair of separated qubits, one in Pasadena, the other in Andromeda, we are nevertheless powerless to predict what we will find when we open one of the boxes, say in Pasadena. Now that's different from ordinary correlations. For ordinary systems, if you know everything about the whole, then you know everything about the parts as well. But with quantum entanglement, that's not so. Even when you have the most complete knowledge of the whole, you have great ignorance about the parts. It was Schrdinger who suggested using the word entanglement to describe these unusual correlations. And he also said it is rather discomforting that the theory should allow a system to be steered or piloted into one or the other type of state at the experimenter's mercy in spite of his having no access to it. What Schrdinger meant is, it seems rather odd that it's up to me to decide whether to open door number 1 of my box and then know what my friend would see if he opened door number 1 of his corresponding box, or I could open door number 2 of my box and then know what my friend would find when he opens door number 2 of his box. But Schrdinger understood, as did Einstein, that these correlations, although they are different from usual ones, do not allow an instantaneous signal to be sent from Pasadena to Andromeda. When my friend opens his box in Andromeda through either door, he just sees a random bit. And that doesn't reveal to him any information about an action that I took in Pasadena. So these correlations, though different from the classical ones that we normally encounter, do not allow us to instantaneously send a signal that carries information. Now, the theory of quantum entanglement did not advance very much for the next 30 years until the 1960s, when, through the work of John Bell, we began to think about entanglement in a somewhat different way, not just as something weird and unsettling and disturbing to Einstein, but as a resource that can be used to do useful things that wouldn't otherwise be possible. What Bell described, though I won't go into the details, was a kind of game that two players can play. The two players, Alice and Bob, are cooperating with one another. They're trying to help each other win. And the way the game works is that Alice and Bob each receive inputs, and they are then supposed to produce outputs which are correlated in a way that depends on the inputs that they receive. But under the rules of the game, Alice and Bob are not allowed to communicate with one another between when they receive those inputs and when they produce the outputs. They are permitted to use correlated pairs of bits that might have been distributed to them before the game began. For this particular version of the game, if Alice and Bob play the best possible strategy, they can win the game with a probability of success of 75% if we average uniformly over the inputs they could receive. But there's also a quantum version of the game. In the quantum version, the rules are exactly the same, except now Alice and Bob are permitted to use entangled pairs of qubits when they play the game, and that enables them to play a better quantum strategy which wins the game with a higher probability of success than they can do with ordinary correlated bits, with a probability of success about 85% instead of 75%. So they've used the entanglement as a resource to do something, in this case win the game, with better success than they could have if they didn't have quantum entanglement. And experimental physicists have been playing this game for decades and winning with this higher probability, which Bell pointed out the laws of quantum mechanics allow. So these super strong correlations, stronger than classical ones, really are part of nature's design. Now, Einstein derided quantum entanglement. He called it spooky action at a distance, which sounds especially derisive if you say it in German. But it doesn't matter whether Einstein likes it or not. Nature is as experiments reveal her to be, and we must learn to love her as she is. So I insist, the boxes are not like the sockses. With boxes, we can do things that we can't do with sockses alone. In particular, we can win this game with a higher probability of success, 85% instead of 75%. Pretty cool, right? But is that really such a big deal? Yeah, it really is a big deal. And we can begin to appreciate why it's a big deal if we think about systems with more parts. Imagine a book. Suppose this book is 100 pages long. It's an ordinary book. It's written in bits. And when you read the pages one at a time, each time you read another page, you know another 1% of the information content of that book. So by the time you've read all 100 pages, one at a time, you know all the information that's in the book. But now suppose it's a quantum book. It's written in qubits instead of bits, and the pages are very highly entangled with one another. Well, in that case, when you look at the pages one at a time, you'll just see random gibberish. Just like with the two entangled qubits, when you open one of the boxes, you just saw a random bit. That doesn't reveal any information about what's in the book, any information that distinguishes one highly entangled book from another. And that's because the information doesn't reside in the individual pages. There's a lot of information in the book, but that information is encoded almost entirely in the correlations among the pages. And if you want to read the book, you have to read collectively many pages at once. Reading the pages one at a time doesn't work. And what's so interesting is that these correlations are very complex in the sense that if you wanted to give a complete description of all the correlations among the qubits, when you just have a few hundred or so qubits, to write down that description using bits would take more bits than the number of atoms in the visible universe. We just can't express in terms of bits the content of this quantum state of a few hundred qubits. And that property seemed very remarkable to the physicist Richard Feynman. And by the way, today is Feynman's birthday. He would have been 99 today. Feynman said, back in the early 1980s, maybe if we operated a computer that processed qubits instead of bits, then we'd be able to perform tasks that couldn't be performed with ordinary digital computers. What Feynman had in mind was that if you can't even express in terms of bits the information content of a few hundred qubits, then by processing the qubits rather than bits, you should be able, or may be able, to perform a computation which couldn't possibly be emulated by any digital computer. And at the time that Feynman was making this suggestion, there was an undergraduate student at Caltech named Peter Shor studying mathematics. And like all our undergraduates, he learned quantum physics as a sophomore. That's part of our core curriculum at Caltech. And like many of our undergraduates, he retained what he learned. And a few years later, he drew on that knowledge to make a remarkable discovery. Shor considered the problem of finding the prime factors of a composite integer, which is the product of two large prime numbers. That's an example of a problem which we think is hard for digital computers to solve. It becomes intractable when the numbers are, say, of order 1,000 bits long. But Shor discovered that if we had a quantum computer, then this would become an easy problem. Not much harder than multiplying numbers together to find their product. And when I heard about this discovery in 1994, I was really awestruck, because what it means is the difference between hard problems and easy problems, the difference between problems we'll be able to solve with sufficiently advanced technology and problems that we'll never be able to solve in the future, that boundary between hard and easy is different than it otherwise would be because we live in a quantum world, not a classical one. And I thought that was one of the most interesting ideas I'd ever heard in my life. And pondering it led me eventually to change the direction of my own research from elementary particle physics to quantum computing. Now, does anybody really care whether factoring is a hard problem? Yeah, there are people who care. Because the hardness of factoring and other related number theoretic problems, which can also be solved by a quantum computer, the presumed hardness of such problems is the foundation of the public key crypto systems that we all use when we want to communicate privately over the internet. In a few decades, if quantum computers are widely available, as I expect they will be, we won't be able to protect our privacy that way anymore. There are alternatives, but it's still not quite clear what will be the best way of protecting privacy in this coming post-quantum world. From a broader point of view, the important thing that we learned from Shor and others is that there's an interesting classification of problems. There are problems which we could call quantumly easy and classically hard. Too hard to solve with ordinary digital computers, but potentially solvable using quantum computers. And it becomes a compelling question to understand better what are the problems in this intermediate class. And we've learned some things about that in the last 20 or so years. But I would say, from the perspective of a physicist like me, what's most important about quantum computing is that with a quantum computer, we believe, though we don't know this for sure, that we would be able to efficiently simulate any process that occurs in nature, which isn't true of digital computers, which are unable to simulate highly entangled quantum systems. And that means that we would be able to simulate the chemistry of complex molecules, if we were seeking new pharmaceuticals, the properties of exotic materials with potentially remarkable properties. But we'd also be able to solve fundamental physics in new ways, for example, by simulating the high-energy collisions of strongly interacting particles, or the properties of nuclear matter, or the quantum behavior of a black hole, or the conditions in the universe right after the Big Bang. So a lot of effort has been put into working out, discovering new applications for quantum computers in recent years. One of the leaders in that effort has been a friend of mine named Eddie Farhi. And a few years ago, when he published a beautiful paper on a new algorithm, he had discovered I was inspired to write a poem which read in part, "We're very sorry, Eddie Farhi. Your algorithm's quantum. Can't run it on those mean machines until we've actually got them." And the poem goes on, but you get the idea. There's a lot of great work being done on developing applications for quantum computers, but as of today, although we have small quantum computers, we don't have ones which are big enough to solve the hard problems which are beyond the reach of today's digital computers. So why is that? Why don't we have powerful quantum computers already? Well, one of the obstacles that we have to surmount to realize large-scale quantum computers is what we call decoherence. Physicists like to imagine a cat which is both alive and dead at the same time. But whenever we look at a real cat, it's always completely dead or completely alive. Now, why is that? Well, the reason is that there isn't any way to perfectly isolate a cat from its surroundings. And those interactions with the environment, in effect, immediately measure the cat. And that projects him onto either completely dead or completely alive. That's the phenomenon of decoherence. And decoherence helps us to understand why, although quantum physics holds sway at the microscale, nevertheless, the things we experience in everyday life are well described by classical physics, because decoherence occurs very rapidly, masking the underlying quantum behavior. Now, a quantum computer isn't going to be a cat, but it too will interact with its environment, even though we might try hard to prevent that. And those interactions will drive decoherence, cause the quantum information we're trying to process to decay, and that will lead to errors in our computation. So if we want to carry out a large-scale quantum computation, we'll have to figure out how to protect a quantum computer from the damaging effects of decoherence and other sources of error. Of course, errors can be a problem even in ordinary life. We all have bits that we cherish. Everywhere, though, there are dragons lurking who delight in changing the values of our bits. So our information can get damaged, but we've learned ways of protecting ourselves against such dragons. If I have a bit which is very valuable and I want to protect it, I can store backup copies of the bit, and then a dragon might come along every once in a while and change the color of one of the balls. But I can ask a busy beaver to frequently check the balls to see if all three are the same color, and when he sees that one is a different color from the others, he quickly repaints it so they all match again. And that means that if the dragon hasn't had a chance to change the color of two of the balls, the information is protected because we've encoded it redundantly. And we'd like to use that same principle that redundant storage provides protection against damage for quantum states. But at first there may appear to be difficulties because, as I already mentioned, we can't copy unknown quantum states accurately. We can't, in the middle of a quantum computation, make a copy of the state of our quantum memory, just in case the original gets damaged. And furthermore, there are more things that can go wrong with quantum information than with ordinary classical bits. With a qubit, it might be that a dragon comes along and opens door number 1 and changes the color of the ball and recloses the box. So that would be like a bit flip that occurs with classical data. But on the other hand, the dragon could decide to open door number 2 and change the color of the ball and reclose the box. We call that a phase error in quantum information. It really has no classical analog. But if we're going to protect quantum data, we have to protect against both the ordinary bit flips and the phase errors. There's another way of thinking about these phase errors. It might be that the dragon comes along and opens door number 1 of the box, and instead of flipping the bit, observes the bit and remembers what he observed. That will have the effect of flipping the color of the ball when we view it through the complementary door, door number 2. And in many physical settings, it's easier for the environment to remember a bit than to flip a bit, and that means these phase errors are a particularly pervasive problem in many physical situations. So really the essential problem is quantum information is very fragile. When you observe it, you damage it. And it doesn't have to be you who observes it. Anyone who observes it will damage it, including those interactions with the environment. If we want to resist decoherence, we have to prevent any information about the quantum state from leaking to the outside world. We have to prevent the environment from learning about the state. Otherwise, the quantum data will be damaged and our computation will fail. So really what we need to do is to keep the information that's being processed almost perfectly isolated from the outside world. And that sounds impossible because our hardware is never going to be perfect. But we've learned in principle how to do it using the idea we call quantum error correction. If I have a qubit that I want to protect, what I can do is encode the information in that qubit in a highly entangled state of 5 qubits, say. See, our enemy is entanglement. It's really entanglement between the environment and the qubit that causes decoherence. But the way to fight entanglement is to use entanglement. We should use an encoding in which the qubit that we want to protect is encoded in the form of entanglement involving many qubits. And then the dragon might come along and interact with one of the boxes, make any observation he wants on one of the boxes. But he won't, by doing so, be able to acquire any information about the encoded state. It's just like the book that was 100 pages long. When you looked at the pages one at a time, that didn't tell you anything about the information content of the book. And so it should be with a robust encoding, which allows quantum error correction. And now the beaver can come along and make a clever collective observation on all the boxes, figure out what damage has occurred, and correct that damage. But in doing so, the beaver doesn't have to learn anything about what the encoded state is, and so it need not be damaged. So the basic idea of quantum error correction is that if we want to protect quantum information from damage, in particular from decoherence due to interactions with the environment, then what we should do is encode the information in a highly entangled state, a system with many parts such that when you look at the parts one at a time, the information is not revealed at all, just like that 100-page book, where you couldn't find out anything by looking at the pages one at a time. The environment looks at the parts of the system one at a time, and it can't acquire the information or damage it. So although we may never see a real cat, which is kept alive and dead at the same time for any significant length of time, we should, in the not-too-distant future, be able to prepare an encoded cat, which is half dead and half alive, and maintain it in that state for as long as we please. So when we first understood these ideas of quantum error correction back about 20 years ago, it was exciting. One of my students at the time who worked on this subject was Daniel Gottesman, and he decided to write a sonnet about quantum error correction, and this is just part of it. We cannot clone perforce, instead we split coherence to protect it from that wrong that would destroy our valued quantum bit and make our computation take too long. And because it's a sonnet, it goes on. But you get the idea that it was a very beautiful notion, quantum error correction. Theorists were excited, but 20 years ago, it was not something that we could immediately head into the laboratory and realize. But that's in the process of changing. Now we really do have quantum computing technologies which allow us to implement this idea of quantum error correction, and I think we'll be seeing many examples of that in experiments in the next couple of years. Now, another hero of this story of quantum error correction is my Caltech colleague Alexei Kitaev. We first met on Alexei's first visit to the US about 20 years ago when he came to Caltech, and he gave this seminar. And I recall that as one of the most exciting days of my scientific life, because I realized I was hearing from Kitaev ideas about quantum error correction which are potentially transformative. And the key thing I learned from Kitaev was the connection between quantum error correction and topology. Now, mathematicians use the word topology, meaning properties of an object which remain invariant if we smoothly deform the object without ripping or tearing it. So to a topologist, a donut and a coffee cup are equivalent. They both have one hole, the one in the center of the donut and the one in the handle of the coffee cup. So when we think about performing a protected quantum computation, what we have in mind is we want the way the computer acts on that protected data to be invariant if we deform the computer by introducing some noise. And that suggests that we should use physical interactions with topological robustness in order to implement quantum computing and protect it from various sources of error. Now, we know of such interactions in physics. One famous old example is what we call the Aharonov-Bohm effect. We can imagine a charged particle like an electron, which is transported around a magnetic flux tube, and that changes the quantum state of the electron by what we call the Aharonov-Bohm phase, which depends on the magnetic flux inside the tube, even though the electron never directly visits the region where the magnetic field is non-zero. That property, that Aharonov-Bohm phase, is a topologically robust property in the sense that we can deform the trajectory of the electron without changing the result. All that matters is that the electron was transported once around the magnetic flux tube. Now, in a two-dimensional medium, which we can engineer by, for example, confining electrons to a two-dimensional interface between two slabs of semiconductor, there are a very rich variety of these topological interactions that can occur. In a two-dimensional system, we can have what we call non-abelian anyons, and they have the following key property, that you can have a system with many of these particles, the anyons, and there can be many distinct quantum states of the particles, but when you look at the particles one at a time, all of those states look exactly alike. You can't tell which state is which when you visit the anyons one at a time. So that's just the kind of encoding of information we would like to have if we want the information to be well protected against decoherence, which will interact with the anyons typically one at a time rather than collectively with many anyons at once. And furthermore, we can process the information carried by the anyons by performing exchanges of the particles in which they swap places. So following Kitaev, we can imagine operating a topological quantum computer, which we could initialize by preparing in some two-dimensional medium that we can engineer many pairs of anyons. And then to process the information, we perform a sequence of exchanges of the particles so that their world lines in 2 + 1 dimensional space-time trace out a braid. And then when I want to read out the result of the computation, I can bring the particles together in pairs and observe whether they annihilate and disappear or not. It turns out that if the anyons have the right properties, then any quantum computation can be performed this way. But the beauty of the idea is that the computation has an intrinsic robustness against decoherence. As long as we keep the temperature low, so there are no unwanted anyons diffusing around, and we keep the anyons far apart from one another, except at the very beginning when they're created and the very end when they're brought together for readout, so there's no unwanted exchange of quantum information between the anyons, then as long as we execute the right braid corresponding to the computation we want to perform, we will get the right answer. That, at least, is the theorist's dream of a topological quantum computer. It's an idea I liked enough that I wrote a poem, which read in part, Alexei exhibits a knack for persuading that someday we'll crunch quantum data by braiding, with quantum states hidden from where no one can see, protected from damage through topology. Enneon, Enneon, where do you roam? Braid for a while before you go home. And the poem goes on, but you get the idea. For a theorist, it's a very exciting idea. But when it was proposed 20 years ago, it was ahead of its time. Alexei and I talked to many experimentalists who thought the idea was very interesting, but nobody was rushing into the lab to try it out. And that's in the process of changing. So how do you turn this theorist's dream into something you can really build? Actually, you can use another idea that came from Kitaev, an idea that under the right circumstances, it's possible to split an electron in half. Now, you think that sounds ridiculous because you know an electron is really an elementary particle. It's indivisible. But in a highly entangled environment, amazing things can happen. In a system of many entangled electrons, it's really possible for an electron to split into pieces. A situation in which you can do that is the following. So imagine a superconducting wire. Superconducting means that it conducts electricity without resistance. And many materials become superconducting when cooled to a low enough temperature. But there are actually two types of superconducting wire, the ordinary type and a much rarer type called a topological superconductor. And if I have a segment of topological superconductor in between two pieces of conventional superconductor, then at the boundary between the two, at the endpoints of this segment, there reside objects we call Majorana modes, or just Majoranas. And what happens is, if you add an electron to that wire segment, the electron dissolves and disappears and can't be detected. But at the same time, the state of the two Majoranas at the ends changes. However, that change is something that you can't observe locally. If you look at the Majoranas one at a time, then you won't be able to tell that the pair of Majoranas has changed its state. So that's just the type of encoding of information we would like to protect against decoherence, a non-local encoding of a qubit. And there have been a number of recent experiments with a lot of the initiative and funding for this thrust of research coming from Microsoft that have indicated that this idea of topological storage of information in a quantum wire really can be realized in systems that people can build in the laboratory, though more experiments will be needed to make the case truly conclusive. Of course, we'd like to do more than store information. We want to be able to process it. And here's one way that could be done. We could imagine a network of wires with T-junctions. The position of the Majorana can be changed with voltage gates under the system. So we can imagine parking one of the Majoranas around the corner, moving the one on the right over to the left, and then unparking the first one, which would be an exchange of these two enneon-like particles. That would be one step in a protected quantum computation, taking advantage of the topological properties of the Majoranas. This type of experiment has not yet been successfully carried out, but I think it's likely that it will be in the next couple of years. And that will not just be a step towards potentially powerful technology, but a real milestone in basic physics. And in fact, some of the underlying ideas that this theory of enneon builds on came from the pioneering work of David Taulis, the great University of Washington physicist, who recently won the Nobel Prize for his work on topological matter. Now, I don't want to give the impression that this exotic topological hardware is the only way people are pursuing to realize scalable quantum computers. That's far from the case. There are a number of different quantum hardware approaches that are being explored and are steadily advancing. I already mentioned the possibility of storing a qubit in a single photon. Another possibility is to store the information in a single atom, where we might imagine the atom is either in its ground state or in some long-lived excited state corresponding to the two states of the qubit. And it's a remarkable encoding because we're storing the information at the level of single atoms, and yet those atoms can be very accurately manipulated with laser light. And in fact, the foundations of the science of manipulating such single atoms were laid at the University of Washington by another great physicist, Hans Dehmelt, who just passed away a few months ago at the age of 94, another Nobel laureate. Another possible encoding is to encode in a single electron, which has a magnetic field, and that magnetic field can be oriented either up or down, corresponding to the two states of a qubit. That's a remarkable encoding. Now we're manipulating the information stored by a single electron, and yet the technology has been developed to control the state of that single electron and protect it pretty well from decoherence. And another approach is to use superconducting circuits, not the exotic topological ones I described a moment ago, but conventional superconductors, where, although in practice there are better ways of doing things, you could imagine the qubit being encoded in the circulating current in a superconducting wire being oriented either clockwise or counterclockwise. And that's a remarkable encoding, because in this case, the information, the qubit, is really being carried by the collective motion of billions of electrons, and yet it behaves, for the purpose of information processing, like a single atom or electron, which can be very accurately manipulated. So really, we're living in an interesting time. Quantum computers today are too small to solve really hard problems. We have quantum computers with of order 10 qubits. We can perform hundreds of operations. We want to scale that up a lot, eventually to millions of qubits or more. But in the near future, in the next couple of years, we expect to have quantum computers with 50 or more qubits. And that's an interesting number, because that means a sufficiently large quantum system that we can no longer simulate it using our digital computers. So potentially, systems with 50 or more qubits could perform tasks which surpass what we could do with digital computers. That would be the onset of the era of quantum supremacy, where quantum systems are performing tasks we couldn't hope to do classically. And I think we should view that really as the onset of a new frontier of the physical sciences, what we could call the complexity frontier or the entanglement frontier. It's different than the short distance frontier we explore in particle physics or the long distance frontier of cosmology, but like those, very fundamental and exciting. We are just in the present era developing for the first time on Earth the technology to build and control precisely highly entangled systems with many particles, which are so complex that we can't simulate them with our digital computers. And that opens new opportunities for discovery of new phenomena. Just as in particle physics, when we build an accelerator that explores physics at shorter distances, or in astrophysics, we build a more powerful telescope, we expect to find new phenomena. And now, as we explore this entanglement frontier, surely that will lead to many discoveries. What are we going to do with the small quantum computers, which have 50 or more qubits that we expect to have quite soon? Well, there are a number of things that people are going to try to do with them. Perhaps the most important is to use the small quantum computer to learn how to make a bigger quantum computer, in particular by trying and perfecting methods for doing quantum error correction to protect against decoherence. But there are other ideas about how they could be used to solve some optimization problems with speed-ups over classical systems, or to solve problems in computational chemistry. We don't really know for sure how well that's going to work, because these small quantum computers won't have quantum error correction. We won't have enough physical qubits to encode information with enough redundancy to do quantum error correction, and we'll just have to see how well it works. And perhaps the most important thing we'll wind up doing as our quantum computing technology advances is discover new applications which we haven't had the imagination to think of before. Now, what about really big quantum computers that can solve the types of hard problem that, for example, would break the RSA public key protocol? RSA, as it's practiced today, is founded on the difficulty of factoring a number with 2048 bits. And I said you couldn't solve that classically, it was too hard. But I was exaggerating a little bit. Because actually, if you were willing to cover a quarter of the land area of North America with a server farm, and you were willing to wait 10 years, you could solve this problem. Now, granted, that server farm would cost $1 million trillion. But the really bad news is that with current chip technology, it would consume 1 million terawatts, so it would use up the world's supply of fossil fuels in just a day. So compared to that, the quantum computer looks pretty good. If we just took the quantum technology we had today and more or less tried to scale it up by brute force, what can we say? This estimate was done by John Martinez, a physicist who's leading the charge with superconducting circuits for quantum computing. And if we wanted to solve this problem, we would need about 10,000 logical qubits, that is, well-protected qubits where decoherence is well controlled. And with the performance of the qubits that we have today, that would mean to do quantum error correction, we need about 10 million physical qubits. Well, the bad news is that would cost, based on the cost today of making one really good qubit, which is about $10,000, $100 billion. But there's good news. You could solve the problem in less than a day, and you'd only need 10 megawatts of power. So the cost is going to have to come down. But that will happen. Not right away, but it will happen. So I've been focusing on 3 questions about quantum computers. Why would we build one? I think the best answer we have to that question is we think that with quantum computers we'd be able to simulate any process that occurs in nature. Can we really build one? Well, we're not aware of any insurmountable obstacles now that we understand the principles of quantum error correction. And how will we build one? Well, as I've said, there are a number of different approaches to building quantum hardware that are under development, and it's important that we pursue these different approaches in parallel. Different quantum technologies could have different applications, and it may be some hybrid of different technologies which gives us the best path to scalability. Now, these questions make for a very interesting research agenda, and I've actually spent a lot of my effort over the last 20 years working on these questions. But I'm not an engineer, I'm a theoretical physicist, and what really interests me are the ways in which our ideas about quantum computing are giving us fresh approaches to a number of the hardest problems in basic physics. So you can see evidence for that by observing that the community of people who work on elementary particle physics and quantum gravity have shown a surge of interest in quantum information concepts like entanglement and quantum information processing in the last few years. These people think that ideas like quantum entanglement are relevant to the problems that they care about. So why is that happening? Well, for the quantum gravity community, it's happening in large part because quantum information ideas are giving us deeper insight into one of the most profound ideas in theoretical physics. That's what we call the holographic principle. The holographic principle was originally formulated because we were trying to wrestle with very deep puzzles about the quantum behavior of black holes, in particular arising because of the quantum entanglement between the inside and the outside of the black hole. And that led to the assertion that information in space is encoded in a way that may surprise you. According to the holographic principle, the information in a room like this auditorium, stored in our brains and our smartphones, is actually available, but in some highly scrambled form, which is extremely hard to read, on the boundary of the room. the walls and the floor and the ceiling. Yes, it doesn't seem that way, but if our current ideas about quantum gravity are on the right track, something like that is really true. And what's becoming clearer in recent years is that the holographic principle is really about quantum entanglement. That is, we can think of the geometry in the room, the information about who is sitting in proximity to other people in the auditorium, as being an emergent property of the quantum entanglement in that very scrambled realization of the information on the boundary. In that sense, we can say that entanglement is the glue that's holding space together. Last year, we had an event at Caltech where Robert Digraph, the director of the Institute for Advanced Study, gave a very inspiring talk. And near the end of his talk, he showed this slide, which was intended to illustrate how the central ideas of theoretical physics are related to one another. And I was quite struck that he put quantum information right in the center of things. I don't think Digraph would have done that a few years earlier, because this idea that quantum information is a unifying principle in physics is really starting to get traction in the last couple of years. But I would go further than Digraph. I would like to erase the word theoretical, because quantum information is an experimental subject, a very active experimental subject. And if it's true, for example, that we can think of the geometry of space and time as an emergent property associated with highly entangled quantum systems, then we ought to be able to get insights into the quantum physics of space-time by doing experiments with such systems in the laboratory. So I expect that in the next few decades, we will advance our understanding of quantum gravity by doing laboratory experiments with highly entangled systems that, in a sense, on a tabletop in a lab at a place like the University of Washington, we will be able to create space-times that didn't exist before and study and ultimately understand their properties. Now, whether that prophecy will really come true or not, I can't say for sure, but I think we can say with great confidence that as we embark on the exploration of the entanglement frontier, many surprises lay ahead. Thanks a lot for listening.
Thanks for that great lecture. I hope that at least it inspired the poets in the audience to learn quantum physics. We have time for questions and answers. There are microphones at the bottom of the stairs. If anybody wants to come forward and ask some questions, please go ahead.
Great lecture. Thank you.
Thanks.
See.
I'm wondering about the application of this wondering about the application to modeling natural systems. Specifically, what came to mind was the atmosphere, or atmospheres, or phenomenon like that. And I was wondering, does chaos theory place some limitations on what you can model successfully?
So the question is, I talked about how with quantum computers, we should be able to efficiently simulate anything that occurs in nature. But what about what we know from chaos theory, that systems that exhibit chaos, and many systems do, the example you suggested was the atmosphere, where the flipping of a butterfly's wings can determine whether there's going to be a hurricane 10 days in the future, or well, maybe a few more than 10 days. Well, doesn't that mean there's a limitation on the simulation because of that sensitivity to initial conditions? Well, that's right. But that sensitivity to imprecision in the initial data is the right physics. That's how the physical system behaves. It exhibits chaos, and if we tweak it a little bit, it will wind up a sufficiently long time in the future in a much different state than if we hadn't tweaked it. And the same thing will happen in the simulation. And so I'll stick by my story, but it is true that we have to be mindful of the limitations on what questions we can answer through such simulations.
Thank you.
Does anybody else have any questions? Mike.
If nobody else is going to step up, I'll ask one. Sure. Do you want me to go? I'd love to, I understand it's not the thrust of your research or the talk, but maybe you can give the folks in the audience a feel for who are the major players in actually making this experimental reality or technological reality? How many qubits could we hope to string together at, say, a Google or Microsoft or an IBM at the end of the year or 5 years out? And then what can you really do with that?
So the question was, what can I tell you about who the players are and how far we expect them to get in building up larger and larger quantum computers in the next few years? And the premise of the question was correct, that there's been a notable ramping up of investment by industry in quantum technologies in the last couple of years. And specifically, you mentioned 3 good examples: Microsoft, IBM, and Google. So I mentioned Microsoft in passing. They are very heavily involved in the quest for Majoranas and topological quantum computing. And I tried to give some indication of where I think things stand, that I think we will have more convincing experimental evidence for robust storage in these Majorana systems, on the time scale of a year, on the time scale of a couple of years, a convincing demonstration of topological information processing in such systems. As far as scaling beyond that, well, all these things are incredibly hard, and it's hard to predict how quickly things will advance. You also mentioned IBM and Google, both interesting examples because they're both pursuing the quantum computing with superconducting circuits and have aspirations to reach the magic number of 50 or so qubits on a time scale of a year or 2, and I think that's likely to happen. And maybe, scaling up to a few hundred qubits with more or less existing technology can happen fairly soon. Beyond that, there are some really big engineering challenges that have to be addressed, and I think that's going to happen. But, it really, the type of quantum computer I mentioned at the end, which could break RSA, for example, that could still be decades away.
So I had a question over here to your left. So there are 2 main different kinds of quantum computers that you mentioned that are in use right now, they're being pursued by Microsoft and Google, were the topological computer by Microsoft, and then Google and IBM are going for the superconducting circuit kind of quantum computer. I had a question about the difference in the number of error-correcting qubits that are needed for the different approaches. You had the numbers 10,000 qubits and 1 million if you accounted for the error-correcting qubits. What kind of, how much would you need for a topological quantum computer in that kind of a scale?
So the question was, can I compare some of the different technologies as far as the overhead cost of doing quantum error correction, since I had, in the example, mentioned a number of physical qubits, which was a factor of 1,000 or so more than the number of logical qubits, and would that apply to other hardware platforms? Well, to get that number, a couple of things go into it. One is how noisy is the hardware that we're going to use, because the better it is, the less the overhead costs. I mean, if it were perfect, then we wouldn't have to do quantum error correction at all. But we can successfully control the errors with less redundancy as the hardware gets better and better. So that was based on a particular estimate, just a little bit better than what's been experimentally demonstrated so far with superconducting circuits. And if the hardware gets much better, then that cost can go down a lot. And I think the right way to think about, then you asked about topological quantum computing. I think the right way to think about that is that we'll always want to have better qubits. If we have better qubits, then we can go further, and in particular, we can get by with less overhead cost and doing fault tolerance. And the topological approach aspires to realizing really good qubits and really good gates. There's some caveats that I didn't go into. And so part of the question, well, so I believe that if you're going to make a topological quantum computer scalable, you'll still be doing quantum error correction on top, kind of at the software level, as well as incorporating it in the physical level. And actually, I think as time goes by, that distinction between doing the error correction sort of built into the hardware, which is the idea of topological quantum computing, or doing it through clever circuit design, or if you like, at the software level, I think that distinction will sort of blur over time. That the topological ideas are already being used in the design of some of the software approaches, and we will probably find other ways to improve the hardware by incorporating quantum error correction into the design of the hardware itself. So that's actually where I think the field is going to go. Eventually, we will have much better qubits than we have now, and it won't be just by incrementally improving the qubit technologies that we're using now, but by incorporating new ideas into the design of the qubits. And the topological approach with Majoranas in particular is an attempt to do that. If it's successful, then of course that overhead cost of quantum error correction above that will be much lower.
So you mentioned how the better computing power is going to eliminate one of our secure communication methods by making killing the RSA algorithm. Can we count on developments in quantum computing, or at least quantum information theory, to give us back another secure channel through entanglement and transmitting entangled bits?
So I'm not sure I heard the first part. Tell me if I have it right. You're asking about the possibility of using quantum technology to protect privacy. I talked about the possibility that when quantum computers are widely available, we won't be able to do RSA. And so there are two rather different paths that we could then follow. One is to, as I think you were suggesting, use quantum information for the purpose of doing cryptography. This is a great idea. And the essence of the idea is, and this is one of the important ways in which quantum information is different from classical, is that you can't observe quantum information without disturbing it. And that means with quantum communication, it's possible to test whether someone has eavesdropped on the communication. That's the idea of quantum cryptography. And maybe the world will go that way. It means, building up the infrastructure so that we can all do quantum communication with one another. And in principle, then we can base security not on the assumption that it's too hard to do a computation that would break the protocol, but the security would really be founded on the laws of physics. And just the validity of the laws of physics would be enough to assure us that it can't be broken. The other possibility, though, is that we will not be using RSA, but other classical public key protocols, which are hard to break for quantum computers. And there are a few candidates for that, but it's going to take some time, I think, for the world to be sufficiently confident that these alternative classical protocols are resistant to attack by quantum computer before we'll make a big investment in setting up a new public key infrastructure.
Hi. So I have kind of a question about the scope of quantum computing algorithms. So are there potentially quantum computing algorithms that would perform better, so from a theoretical standpoint, perform better than classical algorithms for all problems? Or is it perhaps just a subset of problems that could be solved better with quantum computing?
So the question is, can quantum computers improve solving any problem, or is it just special problems for which they give significant speed-ups? Yeah, it's important to understand that quantum computers do have limitations. And in particular, we don't expect that quantum computers would be able to dramatically speed up the solution to problems that we call NP-hard. The NP-complete problems are the ones that are the hardest in NP, which means the hardest for which we can check the answer by doing a classical computation. And for the hardest problems in that class, which are very common and which people often want to solve, combinatorial search problems, the traveling salesman problem is an example, we don't think a quantum computer can provide a super polynomial speed-up of the solution to that problem, as it can for factoring, for example. That's because for such combinatorial search problems, in the worst case instances, we don't know of a method which is much better than just an exhaustive search for the solution. And quantum computers can speed up exhaustive search, but they only speed it up quadratically, that is, with the quantum time to solution going like the square root of the classical time. And so for problems like that, there may not be a quantum speedup which is any better than that quadratic speedup, and well, that would be a much less spectacular advance than for the problems that have the right structure to be amenable to fast quantum algorithms. Now, factoring is an example of such a problem, but as I said, I think the application that we know of, which will have the greatest impact on human society, is simulating quantum systems.
Thank you.
Hi, my name is Jack Woods, and I'm fascinated in the idea of the quantum computer one day being able to simulate physical systems. And I'm kind of curious as to what kind of speed that would be at, say if you were trying to simulate the evolution of a star or a planet or the evolution of life. And if you could just put in a few basic rules and just see what happens, and maybe emergence would show in the solution.
Well, it's, so the question was, I guess you wanted me to say something a little more concrete and specific about how much we could speed up the solution to physical simulation problems. And actually, that's a hard question. There are many cases in which it's not obvious that a quantum computer will, have a big advantage over a classical one for physical simulation. The cases in which we expect the quantum computer to have a big advantage are the cases where many particle quantum entanglement is an important feature of the system. In many cases, that's just not true. So that's why I mentioned, for example, molecular chemistry, where there's a great deal of investment done nowadays in ab initio computational chemistry, but it's very limited what problems can be solved because it's just too hard. The digital computers don't speak the right language to describe the behavior of electrons in complex molecules. And that would be a problem that would be very well matched to the strength of a quantum computer.
First of all, thank you very much for the excellent talk. My question is a follow-up on one of the previous questions. One of the bottlenecks, one of the assumptions that we have with quantum computers is that we're able to build software that takes advantage of that. Previously, you were talking about some problems lend themselves to quantum computing, some don't. My question is about the problems that lend themselves to quantum computing. Peter Shor himself wrote a paper a few years ago saying that we have not discovered as many algorithms in quantum computing as we thought. Can you speak or make some remarks about what some of the specific bottlenecks are in finding solutions, or whether we've overcome those?
Right, so I guess the question is, what can we say about what types of problems, or where to look for opportunities to discover new, fast quantum algorithms?
Can you speak to who is working on these types of problems, and what holy grail types of problems they're trying to solve to break that bottleneck?
Yeah. Well, one thing, so I won't play the chemistry card again, but that certainly is application where there's great potential to have impact. But I mean, there are a lot of people speculate about a lot of things, and in some cases the speculations are, can't be backed up by firm arguments. For example, there's a lot of talk these days about quantum machine learning. I mean, why not put together two buzzwords? But but actually, there's a root idea which is very interesting, which I guess I'll mention. One of the applications, one of the algorithms that we know about is quantum computers can speed up linear algebra. They can solve systems of linear equations. Well, that's not a hard problem, but they can really speed it up a lot, so that you can solve n linear equations in a time which is a power of a logarithm of n. And now, it doesn't always work. The equations have to have the right properties for that to be true. But, I mean, we're solving linear equations all the time. And so we have this primitive, which looks very powerful, speeding up linear algebra. And if we can find the right nail to hit with that hammer, I think the impact could be very important in a number of areas, including solving optimization problems, training quantum systems to do some of the things we do with classical machine learning and so on.
Thank you.
Okay, I think we have to close the question session now. Feel free to come in to the stage afterwards and talk to John. So let's thank John Preskill again.